Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light, where we have been looking at the work of Thomas Young, his lectures on light and colors. This is in chapter 20 in A Student's Guide to the Great Physics Texts, volume 3, on page 233. And what you remember what we've been doing is we've been going through Young's comparison of the wave and particle theories of light. So this is 1809, roughly, when he wrote this, and he's evaluating the wave theory of light and the particle theory of light that were really developed in the late 1600s, early 1700s. So he's about 100 years past this, and there are different viewpoints on which one's better, and Young is doing kind of a critical analysis of this. So he's going through these arguments, and just so you know, there is one critical experiment that Young is going to be talking about, his two-slit experiment that he did in right around 1809, that is seen as kind of the clincher in providing the strongest evidence in favor of the wave theory of light. Okay, so we'll get to the end of that by the end of this chapter. We left off last time on about page, I suppose it was 238, where he was talking about reflection. And that was, I guess, 237. He was talking about reflection and that both the particle and the wave theories of light were able to account for the law of reflection. That is that the incidence angle equals the reflected angle for light bouncing off of a mirror. And then he goes on in the, I guess, the first full paragraph on page 237 to discuss the law of refraction. So let's talk about the law of refraction, or Snell's law. And he does an analysis of which one of these provides a better explanation of the law of refraction. And he really says that in a sense they both are good at explaining the law of refraction, but there's an important caveat to that. So let's first look at how he explains the particle theory, or Newton's corpuscular theory, if you'd like to call it that. And if you imagine you have a boundary between air up here and glass down here, and according to Newton's particle theory, you have this particle that's flying in with some velocity in this direction, and when it gets near the glass, remember, according to Newton's theory, I hope I said that a moment ago, according to Newton's theory, the glass exerts a force on this particle, and that force that it exerts on the particle is one of attraction. So I'm going to draw by an orange arrow here. This is meant to suggest that there's an attractive force. Okay, and if there's an attractive force, if we think about the motion of this particle of light, it has a horizontal speed and a vertical speed. That's why it's moving diagonally. Well, since the attractive force is downward, the horizontal component or part of the speed doesn't change. By the principle of inertia, it just keeps moving horizontally at the same speed, but because there's a downward force, there's a downward acceleration, and as a result of that, the downward speed increases. So if you draw the trajectory of this particle after this force acts on it, it is now going to be directed more downward than sideways, because it retains the same horizontal or sideways component of speed, but it acquires a downward component of speed, and hence it moves downward. Okay, so that is, in order to bend a ray of light toward the normal, remember this line right here would be the normal, so this ray would be bending toward the normal because the angle of refraction is less than the angle of incidence. In order to bend a ray of light toward the normal, the particle of light must feel an attractive, and in this case that would be downward, force, which speeds up the particle. Because after all, it retains the same horizontal speed, but it acquires downward speed, so overall the speed increases. Okay, notice what this implies is that light does the right thing. It bends toward the normal only if it's moving faster in glass than in the air. So according to this theory, light travels faster in glass than in air. So if it did do that, that would account for the observed trajectory according to the particle theory of light. Now, what about the wave? So it works, but you have to assume the light goes faster in glass than in air. What about in the wave theory? Well, we just went through this at some length in our last, I guess, a couple of chapters ago when we were looking at Huygens. Here, if you have, once again, if you have glass down here and you have air up here, and we think about light not as consisting of rays, or as particles, but as waves coming in like this, well, remember these wave fronts, because the wave slows down, they kink like this, so they bend so that the ray of light was going at a different angle on the outside of the glass and on the inside of the glass. That is, the angle of incidence is greater than the angle of refraction, right? But notice what's different here. Specifically, in order to bend the light ray toward the normal, as is observed, toward the normal, the wave of light must slow down in the glass. That is, moving from air to glass, it has to slow down. So this implies that light travels more slowly or slower in glass than in air. So both of these theories do account for the bending of light according to Snell's law, but one requires the speed of light to be greater in glass, the particle theory, and one requires the speed of light to be less in glass than in air. And what Young points out here is that at this point there is some evidence that light in fact is traveling slower in glass than in air. And if that is the case, that would seem to favor the wave theory of light. So that's the point that he is making here on page 237, the first full paragraph. Okay, so that's refraction. Let's go on and talk about some of the other points that he makes in this chapter. So let's talk about partial reflection. So this is the last paragraph on page 237, the partial reflection. What do we mean by partial reflection? Well, if you've ever stood in front of a pane of glass looking outside, you'll notice that you can sometimes see a faint image of yourself in the glass. That is, the glass acts kind of like a mirror, but presumably, well, obviously, someone standing outside of the window will also see you standing inside, because some of the light that's coming from you goes through and arrives at the person's eye who's outside, and some of the light that's coming from you bounces back and comes to you and forms an image of you. That is what we call partial reflection. If one were to take a particle theory of light, where all these particles are flying like this, what Young points out here is that there is not a good explanation, according to the particle theory, for why some particles would make it through and some particles would bounce back. He said this is a completely unsatisfactory theory. There's no reason why that would be the case, at least no convincing reason, according to Young. But the wave theory of light seems to provide a very nice explanation of this, because after all, we know that waves of sound, when they strike a substance, some of the waves will make it through and some of the waves will bounce back. This happens when, that's why if you have a wall, you get an echo off of the wall, but somebody standing on the other side of the wall still hears some of the sound making it through the wall. So we know that waves are partially reflected from surfaces, but we don't have another instance of particles partially reflecting from a surface and partially making it through. Okay? And then what's the next thing that he talks about? Well, let's jump ahead to page 238. He talks about total internal reflection. I can probably talk about that a little bit up here. I'm trying to take advantage of any space that I have left on my sketchbook here. So let's make a line and talk about total internal reflection. What is total internal reflection? Well, we've talked about this already. If you have a surface that separates air from glass, well, if you have light coming from the glass, if it's coming in at a special angle, it will not come out into the air, but rather it's totally reflected back into the glass. That's total internal reflection. And what Young points out is that this is explained very well by the particle theory or by the wave theory. There's really no way of saying which one's better by looking at total internal reflection. The next thing that he talks about is a phenomenon called phosphorescence. Phosphorescence. And this is, I guess, on page 238, the second paragraph. He talks about chemical combustion and then phosphorescence. What is phosphorescence? Well, if you have something like a diamond, I think he mentions a diamond. I'll draw a little diamond here. And if you illuminate this, so this is a nicely cut diamond apparently. And if you illuminate this diamond with violet light, he mentions, so I'm going to take some purple light. I think this is purple light. If you illuminate it with violet light, what can happen is red light, it can emit red light. Okay? That's the phenomenon of phosphorescence. There's some light that's purple, you shine on it, and then you turn out the lights, and then the diamond will glow with a red light, a different color than the light that you struck it with. And he says that the particle theory doesn't seem to provide a nice explanation of this. After all, if light are particles and the different colors of light correspond to different sizes or masses of particles, they're different kinds of particles according to Newton, then if you're striking it with purple or violet particles, it should be accumulating these, and then when you stop striking it without, you turn the light off. There's no reason why those should suddenly come out as red particles of light. And, I suppose one could talk about transmutation. Newton, in the last chapter, he was a fan of the topic of transmutation. One thing can turn into the other. And Young doesn't seem to take that as perhaps seriously as he should, because Young seems to think that this cannot be explained by the particle theory of light. And rather the wave theory of light, he kind of in an offhand way says that the wave theory of light can explain it using the phenomenon of sympathetic resonance. So this is something when you strike a guitar string and it makes a note, it can make another guitar string vibrate at at the same frequency, but apparently they can sometimes vibrate at harmonics or different frequencies, slightly different frequencies. So he's alluding to the phenomenon of sympathetic resonance to account for this, but he doesn't provide any details. So I find this to be a little bit less convincing than some of his other arguments. Okay, I'm going to have to stop here because I'm out of room, and I'll pick this up next time when I can clear some space.